I'm going to discuss a bit further properties of the Gaussian multiplicative chaos measures. In particular, I want to discuss say exact scale invariance. Moment. I will also give you a few theorems about the moments of this measure in order to play a bit with multifractality. And also the support. Okay, so well, these are a few properties that I will use hopefully in my last lecture. Okay, so tomorrow it will be about criterion for uniqueness, and convergence in probability for convolution cutoff and in the last lecture I will try to prepare something in order to explain the connection between random planar maps (PM), quantum gravity, and Gaussian multiplicative chaos. So, well, more precisely, I will try to show you how to construct the volume form of the that you can put on a random triangulation or quadrangulation, and what should be the scaling limit of this object, okay, when you embed it onto the sphere. Okay. So to construct this measure here, I will have to use a few properties here. So I'm going to discuss them informally today. So the first thing I want to discuss is exact scale invariance. So in the class of all the kernels with correlations of log type, there is a very specific example which is very nice because of its scaling properties. So the thing is that we want to focus on this kernel here. Okay. Usually I get an additional smooth function g here, but I want to get rid of it because of the additive properties of the logarithm. It's like well, if you look at the class of linear integrals, you have a nice process among this integral. It is the Brownian motion because it has a scaling. Okay, it has a scaling, square root scaling, and here among all the Gaussian multiplicative chaos that you may look at, there is a special kernel that will give you a very nice scaling property. So the thing is that I want to consider this kernel, but I want to make sure, you have to make sure that it is a kernel of sigma positive type. And this is true only in dimension 1 and 2. Okay. In dimension 1 and 2. So the thing is that if you want to look at a higher dimension, there exists a kernel K of sigma positive type such that K of xy is equal to the log provided that x and y are close enough. So the issue here is about the extending this function for distances that are larger than 1. Okay, I don't discuss the extension, but well, there is some kernel with this property at short scales. Okay, so so I don't want to show you how to prove that this kernel is of sigma positive type. There are the details in the lecture notes, but you can do a simple calculation in dimension 1. Okay, if you want to see if this kernel is of sigma positive type, you can compute, for instance, the Fourier transform, or you can write it as an integral form and use the Shell relation to extend it as a sum à la Kahn. So I rather want to play with the properties of this kernel. Okay, I want to explain you why it is useful. So the statement is that well, property proposition. Well, let K a kernel with these properties up there. Then the associated GMC, Gaussian multiplicative chaos, is exactly scale invariant. And actually, it would be fair to say stochastically. Because the main difference, for instance, with the Brownian motion, you have if you rescale by lambda your Brownian motion, you will have a square root of lambda coming out of your Brownian motion. The factor is deterministic. Okay, here the factor will be stochastic. Okay? So this means that for all lambda less than 1, so lambda will stand for the scale. The measure m of lambda a. So for all a included in the ball centered at 0 and radius t over 2 is equal in law to lambda to the power g. So this is the deterministic part of the scale, and then you will have say, some stochastic factor. And here A is also included in the ball B0 T over 2. Okay, so in this expression, the factor that you have here is independent of the measure that you have on the right-hand side. So with omega lambda, a Gaussian random variable, with mean 0 and variance log of 1 over lambda, independent of the measure m gamma 8 that you got here. Okay. So this means that if you look your measure at a very small scale, okay, you observe exactly the same measure up to a stochastic factor. Okay? In the same way that if you look at a Brownian motion at a small scale, you observe a Brownian motion up to a deterministic factor, which is the square root of lambda. Okay? But here the factor is deterministic, and it is independent of the measure that you've got here. Okay? So, well, if you want to understand why this is true, this is well, proof. So take a sketch of proof if you want. You take a Gaussian random distribution with kernel well, let me take the kernel log plus, so we are in dimension 1 or 2. Okay? The thing is that if you look formally at the distribution x of lambda x, okay, this is a Gaussian distribution with kernel k of lambda x. Okay, if you just compute the covariance, at least if you test this distribution on smooth function, you will have this covariance kernel. Okay, for this. So, but here you can use the properties of the log. So, if your test function has a compact have a compact support included in the ball B0 T over 2, here. This quantity will just be T log, and this gives you x minus 4. Okay, so here you have a Gaussian distribution which has this covariance kernel. Okay, sorry. 1 over lambda. Okay, so this is the same. This is the kernel of x, and this is the kernel of a Gaussian random variable. Call it omega lambda. Okay, this is a Gaussian random variable with mean 0 and variance log 1 over lambda. Okay, so you have the following relation in law. Okay, and where omega is independent of x. So now you can just compute the measure of a set, provided that it is included in the ball B0 t over 2, and you just get the integral of lambda a Okay, so now I'm going to make a change of variables. So to be correct, this object is defined through a limiting procedure. Okay, so to be correct, I should first consider a cutoff of the distribution x, take the limit, okay, and make the change of variable in the regularized measure and take the limit. Okay, but you can do this. This is a formal proof, but you can make it rigorous. Okay, so now you want to set lambda u equal to x, the change of variables. So you get integral over a of exponential gamma and so we are in dimension 1 or 2, but say the change of variables gives you a factor lambda to the power g, where this is the dimension, and here 1 or 2. Okay, so now you can use the relation in log that we've got here. Okay, so you can say that this is equal to lambda to the power g minus the variance of omega lambda, which is log 1 over lambda. Okay, g u gx. Okay, and this gives you exactly the expression I wrote. So this is lambda to the power g exponential gamma times where the distribution here that you've got here, x is independent of the factor here. Okay, so this is just a simple computation. Is that clear? Okay, so now so we've proved this statement. So why is it important to have such a kernel? Because if you want to analyze the small behavior of your measure, I mean, when you want to look at a very small set, you will write a small set as something like this with a small lambda, and then you'll see that the contribution of the small scale will just appear through the term that you've got here, and this term will not depend on the scale. Okay, so this is very convenient to work with this measure and understand how they behave at a small scale. And then if you can prove some properties with respect to this measure, where the computations are very simple, then you can use a Kahn comparison lemma to extend your properties to to all other classes of kernels, provided that you can bridge the gap with Kahn comparison principle. Okay, so this is, in some sense, this is the canonical behavior of your measure at small scale. Okay. So so we will use this kernel a bit later. Now I want to come back to the moments of the measure, and then I will use this kernel to show you some multifractality properties of this measure. So moments further property. Now I'm going to review a few theorems that you may have in the literature. So in the following, I will take the Radon measure sigma equal to the Lebesgue measure. And the kernel K will be log correlated. I mean, in the general sense. I mean, this is a log plus a function G, which is bounded. So actually, I'm going to state a theorem. If the measure M gamma is non-trivial. So recall that the criterion for non-triviality here is gamma square less than 2D, 2 times the dimension. Then M gamma admits moments of order Q for all Q belonging to minus infinity 2G over gamma square. Well, what does it mean to have moments of order Q? It means that for all compact set A, with non-empty interior, then the expectation by Q is finite. Okay, I take the non-empty interior when Q is negative, because if Q is negative, M gamma, if you take something which has a null Lebesgue measure, M gamma of A is equal to 0, so 1 over 0 is equal to infinity, so for negative moments I have to take a non-empty interior. So, well, this theorem these theorems are not obvious. Mainly, there are two ranges of values here. There are the negative values of Q and the positive values of Q. Okay, there are a lot of works on what is called Mandelbrot multiplicative cascade. This is some kind of similar model, but on a diagetic tree. Okay, and basically, if you look at the they are called the Mandelbrot multiplicative cascades. If you look at the Mandelbrot multiplicative cascades on a tree with a Gaussian weight on the edges of the tree, you get a Gaussian multiplicative chaos à la Kahn. Okay, so that you can use the Kahn comparison principle to transfer the results that you have on the cascades to the Gaussian multiplicative chaos. Okay, so to prove these properties here between 0 and 2G over gamma square, you can use a Kahn comparison principle. Okay, so this results from what we know from cascades, and for Q belonging to minus infinity to 0, this is an adaptation, of a subtle argument of Molchan, which has been used in cascades to prove negative. The existence of negative moments. It works for Gaussian multiplicative chaos, and actually I want to mention two other results that have been proved by Duplantier and Sheffield for the Gaussian free field, and by Mika Nicolai in the case of in our context. Then you can adapt Molchan argument to prove the following small deviation property. So this is a remark, small deviation property. You want to look at the probability that your measure is very small. Say m gamma of a ball is very small. X is small. Actually, this quantity behaves like a constant times exponential log x to the square. Okay. And from this property here, you can prove that your measure has negative moments of all orders. Okay. And this has been proved. So the basic argument is of Molchan, and it has been used by Duplantier, Sheffield for the GFF. It is in the Inventionist paper about UV quantum gravity in KPZ, and Mika Nikolai in a paper small deviation for something. I don't remember the entire title, but you can find the paper on arXiv if you want. Okay, so this is just a remark, but you have a very precise estimate for the shape of your distribution tail. Okay. So, well, these moments are very useful. That's why I'm giving you this theorem. I want to use them, but I cannot prove them during my lecture. It would be too long. Maybe another interesting result by yes. Maybe the constant here, but not the tail here. Not the function here, but maybe the constant here. I'm not sure. Okay. Now another result by Barral and Xiangjin, who is here. It's about the tail of your measure. So it's in dimension 1, so second remark. And k of x well, he played with the scaling properties of this kernel, this very specific kernel, to show that the limit when x goes to infinity of x that the measure applied to a ball. This limit exists and is non-trivial. Okay, so you have the exact shape of the right tail distribution. Well, this is some summary of properties that you can have on this measure. I owe you a proof about the structure of the support. Well, okay. Well, maybe well, I'll do the proof about the structure of the support at the end of my lecture. Now it's a good moment to speak about multifractality. So, well, now I'm going to property to show you that we can compute the behavior of the moments that you've got here for very small sets. Okay, so take a kernel K and gamma square less than 2G. Well, for all Q smaller than 2G over gamma square, there exists a constant CQ such that for all R belonging, well, say small enough, the measure of this is about the behavior of this moment here when R becomes small. Okay, so you have two constants. Let's say 1 over CQ, where psi of Q is given by G plus gamma square over 2 minus okay. So now if you look at the at this moment here, you see that they behave non-linearly. Okay, here the spectrum of your measure is non-linear because of the q square term here. If you make the same computation with the Brownian motion, for instance, you have here a linear function of q, which is q over 2. If you take any monofractal process, you will have a linear function of q. And here, for this measure, you have something non-linear, okay, because of the square. And this kind of behavior is related to. You can relate this behavior to the local regularity of the measure via the Parisi-Frisch formalism and or multifractal analysis. I'm not going to discuss the whole literature, but this means that this non-linearity here means that your measure, their local behavior, is very is non-homogeneous. It depends very much on the point where you are located, and depending on the point, the behavior may be quite different. I don't want to review all the results, but I just want to show you a few examples here. Okay, this is what I'm going to do now. But we can compute these moments here. Okay, we're going to make the proof. Well, the proof actually will be very simple. Well, the first thing is that if you take an exponent q here, well, depending on the value of q, you are convex or concave, and actually you can play with the Cahn comparison principle. You can make that rigorous. You can use this comparison principle to show that you can, whatever the kernel you choose here, the result will be the same. Okay, so it will be well. It is nice if you choose a very nice kernel here. Okay, and if you want to choose the best kernel to make these computations, you have to choose the kernels that are exactly of log, which are exactly log. Okay. So I'm going to make the proof in the case when I just have the log here. So if I just have the log, I have the exact scale invariance property that I mentioned. Okay, so if this comparison principle tells you that you can choose your favorite kernel K, and my favorite kernel is the log. Okay. Okay, so now if you have a log, you know that m gamma of the ball b0 r to the power q. If you take this expectation, and if you your r here is less than 1, you can use the scale invariant of this measure. Okay, because if I choose this kernel, this measure is scale invariant, as I mentioned just a few minutes ago. Okay, so this expectation is just we are in dimension g, so I have my r to the power g exponential gamma so this is the stochastic factor, and m gamma of the ball b01, and everything is to the power q. Okay. So now, by the property of scale invariance, I know that this random factor here is independent of this measure here. Okay. So I can split my expectation. I just have here I have a q, and the variance of this random variable is log 1 over r, and here I have the mass of the unit ball to the power q. So I don't know what this constant is, but it's finite because q is less than gamma square over 2d. Q is, sorry, 2d over gamma square. Okay, so we know that this quantity is finite. Okay. So now I just have to compute this this expectation here, and this is just the Laplace transform of some Gaussian random variable. Okay, so this is an easy computation, and you find that you got r to the power g plus gamma square over 2 times q minus so here you have gamma square q square over 2 log 1 over r, and this gives you the gamma square q square over 2. Okay, times your constant here. Okay, and it depends on q because you have a q exponent in the constant. Okay. So now, yeah. Yes, actually, why do I have a dimension? Well, this is just in my proof. Because if I can choose this kernel only in dimension 1 and 2. Okay, so in my proof I am in dimension 1 and 2, and okay, there is a proof in dimension 3 and higher, because you don't have in dimension 3 and higher, you don't have a kernel like this, but you have a kernel which coincides with the log on the ball, and this is enough for scale invariance, but I don't know what it is outside of this ball. Okay. But the proof is the same if you use another kernel. Okay, so now I'm going to play just a bit with this power law spectrum to show you a few funny properties of this measure. So remember, I told you that Karen showed, recall, that well, that if you take any epsilon positive, so show that if you take well, first the idea. This is what Karen showed. It means that if you take the center, well, we are interested in the growth of balls, okay, and everything depends on the center of the balls, okay. So if there exists a set, a random set, okay, where if you take the center of your ball in this random set and you look at the decay of ball in this random set, you will have this typical behavior, okay. This means that you have your space. Here you have your domain G. Inside this domain, you have some points, and actually they are dense in G, but they have an outdoor dimension which is 2 minus gamma square over 2. Well, they have a small outdoor dimension. And each time you look at a point, so red, this is the support, the carrier of M. This is called the carrier. If you look at the decay of balls when they are centered at a point, at a red point, okay, you will observe typically a behavior of this type. Okay, but this set in red is random, okay? And well, if you, for instance, if you fix a point, you choose your favorite point. So mine is here, but it is not random. This is my favorite point. Each time you give me this domain G, I tell you that this point is my favorite point, okay? And I may want to look at the decay of balls around this point. So my point is not random. And as this red set is very small, I am unlikely to be located inside this red set. Okay, my favorite point will certainly not be in my red set. So we can ask the question: if I fix a point, what is the behavior of the balls around this point? So we can. What I'm going to show is that if X is fixed, so if X is fixed deterministically, it's very important. Then, for all epsilon positive, there exists a constant C epsilon such that the measure of the ball centered at my favorite point are less than a constant C epsilon R to the power 2 plus gamma square over 2 plus epsilon. Sorry, minus epsilon. Okay, so the behavior is quite different from the red area. Okay, on the red area I have a minus here, and on my favorite point I have a plus here. Okay, so we can We can use this proposition to show this. So how can you prove such a statement? But, you just look at the probability. Say, well, just have to look at the probability that your ball, that the measure of your ball is bigger. So I'm going to take, as I'm going to use Borel quantity, I'm going to use a countable number of radius. So I take them small, and I can take 2 to the power minus n. So I just want to show when the measure of my ball is bigger than some quantity. So this is a function of the radius. Okay, the radius is 2 to the power minus n, and I take the power beta, and then I will have some estimates, and I will adjust beta so that I can use Borel quantity. Okay. So so this probability is equal to the same probability if I take a power q with q positive, so that my function x to the power q is increasing, and well, this is obvious that I have this relation. Now I can use the Markov property. Markov, I mean Markov inequality. So you get this estimate to the power q, okay? But now I know precisely the behavior of this quantity, okay? Because this is just what we showed. So this is less than some constant, 2 to the power minus n beta q, and here I just have 2 to the power minus n times the function psi of q. Okay? And of course, I missed my exponent here, because there is a minus here, so a minus here, and here this is a plus, so that I get minus here. Okay. Okay. So now you just have to, if you want to apply Borel quantity, you just have to find some value of q such that this quantity is positive. Okay. So that this probability will be summable. So, well, let's look at the derivative at 0. Actually, the graph of this function psi is like this. So you've got 1 here. You've got the dimension g here. And so here you have and your function psi does something like this. But okay, whatever the slope here, okay, is given by the term here. The slope at 0 is given by the term here. Okay, so if you want to have this function which is positive for very small q, you see that beta must be less than the slope that you've got here. Okay. So if you take, for instance, set f of q is equal to psi of q minus beta q, you see that f of 0 is equal to 0. Okay. And we can compute the derivative at 0. This is equal to 2 plus gamma square over 2 minus beta. Okay. And if I want this quantity to be positive, necessarily beta is less than 2 plus gamma square over 2. Okay. So So now you can use Borel-Cantelli to show that there exists a random constant C call it C, such that m of gamma and beta if beta is less than 2 plus gamma square over 2. Okay, and as the measure of a ball is increasing with the radius, this is not hard to see that this implies that m gamma of every ball with a radius which is less than 1 is less than c r to the power beta, with beta satisfying the same condition. Okay. So and actually this bound is optimal. Okay, you must choose beta less than this quantity here. So this is the first illustration of the fact that you may have different behaviors on different points. So if you look at my picture, this means that if you take a point deterministically, you are much more regular. Your measure is much more regular than its typical behavior. Okay? Because typically the balls behave like this. Okay? The measure, if you sample a point according to the measure, you will typically behave this behavior. But if you don't want to listen to your measure, you choose your favorite point, you are much more regular. Okay. So now we can give you an exercise. The same. In the same along the same edges, you want to have a uniform bound of this type. I mean, you may ask the question, okay, I don't know, depending on where I'm located, I don't know the behavior of my balls. Okay, so maybe you are interested in having a uniform control of the volume of balls. Okay, a uniform Hölder bound. So this is possible. If gamma square is less than 2g, there exists a constant c such that, so the constant is random, such that for all x, say in the ball B01, you can take the ball as large as you want. The measure of a ball centered at x is less than c C R to the power 1/2. Okay. So of course, if you want uniform, so my bound here is uniform on the ball B01. Okay. Whatever the center of the ball you look at, you have this uniform control. So of course, this control here must be worse than all the bound I gave you so far. So how can you prove this statement? I can give you a hint of proof. So now let's look at a square instead of a ball, more convenient. So we are in dimension 2, say. Okay. So instead of so you will divide your square, your unit square, into a smaller square. Okay. Each of these square with size 2 minus 2 to the power minus n. Okay. And instead of looking, this is the same proof as here, but instead of looking at the probability that a ball is bigger than some exponent, you will look at the probability that the maximum of the square on my grid, okay, is bigger than some power. Okay, so you will look at something like this. Call each small square, you call it ckn with a good index for k. So look at this quantity here. And you want to estimate this quantity here, and you will look the correct value for the correct value of alpha. Okay. So you take the power q once again. Power. Use Markov. Then say that the maximum is less than the sum. Okay, you will have a maximum of some quantities to the power q. You say that this is less than the sum over all the terms to the power q. Then you use the estimate on m gamma to the power q. And then you optimize, and you will find the correct exponent close to q to 1. Choose q close to 1, but bigger. So then you can use Borel counting. You can do this as an exercise if you like. So you see that you'll get another control of the measure. Okay? And actually, well, just a remark on my picture. Actually, you may have a wide range of values for x for which m gamma of bx are behave like some power of alpha. You can choose a wide range of values of for alpha, and for each value of alpha, you will have different points, different sets of points on your domain G, and okay, they are all non-empty for continuous range values of alpha. Okay, this is the main idea of multifractal analysis, except that you want to quantify exactly which point in your set D contribute to this power of alpha, how large they are, and so on. Okay. So my time is over, and to tomorrow, so this will be about convergence in probability and uniqueness. And okay. And in the last talk, I will try to cook up something about this random planar math things. Okay. Thank you for your attention. Any questions?